Hello and welcome to our video on reactions involving haloalkanes. So today we'll be first covering the difference between a primary, secondary and tertiary haloalkane. Next I'll be giving you a quick overview on nucleophilic versus free radical substitution reactions. And thirdly, we'll be going over the common reactions you'll need to know in regards to haloalkanes in the Year 12 chemistry syllabus. So, like with all compounds, there is a primary, secondary, and tertiary version of the haloalkanes, which correlates with the number of alkyl groups that are attached to the central carbon. So, with the primary haloalkane, there is one alkyl group, so that could be your R1, if you like. With the secondary haloalkane, there's two alkyl groups, signified by R1 and R2. I've got methyl groups here, but it could be an alkyl group of any length. And with your tertiary haloalkane, you'd have three alkyl groups, which I'll show as R1, R2, and R3. So another way of looking at it is a primary haloalkane will have two hydrogens, secondary one hydrogen, and a tertiary no hydrogens attached to the central carbon. So before we start exploring the difference between free radical and nucleophilic substitutions, so the difference between understanding a free radical and nucleophilic substitutions is really important in being able to differentiate between reactions involving alkanes, alkenes, and alkynes, and haloalkanes, and you'll see that a bit later. There are some key terms, however, that we need to distinguish between before we head into that. So we have the electrophile, the nucleophile, and the free radical. In the video on reactions involving alkenes, alkenes, and alkynes, I did go over the free radical and what it was. I'll go over it again in the way of review. Essentially, it's a molecule with an unpaired electron in the outer shell. And the way you draw it is what I've shown here. So you draw the chemical symbol and a single dot. If there was a double dot, that would indicate that it had a complete outer shell. And since it has a single dot, it's a free radical, due to it having an unpaired electron. So free radicals are extremely reactive. That's the main takeaway from that. Now we have two fairly unfamiliar terms. We have the electrophile. So it's kind of within the name. So electrophile, electron loving. If something loves electrons, it is intensely positively charged. So remember that unlike charges attract. So if it's positively charged, an example being H+, it is likely to get given electrons, or accepting a pair of electrons in order to bond. So electrophiles, positively charged, H+ is an example, likely to accept an electron pair. Nucleophiles are much the opposite. They are negatively charged and likely to donate an electron pair. An example is OH-, which is a negatively charged molecule. So now that you've hopefully understood those three terms, we'll go over the difference between free radical and nucleophilic substitution reactions. At the very basic level, a substitution reaction occurs when one atom in a molecule is replaced by another. There are two mechanisms by which this may occur. There's a nucleophilic substitution mechanism and a free radical substitution mechanism. In the video on reactions involving alkanes, alkenes, and alkynes, we went through a reaction where an alkane would undergo a free radical substitution. And that's kind of what tends to happen. Alkanes will undergo free radical substitutions. Haloalkanes, however, will undergo nucleophilic substitution. So that's a really important point for you to understand in regards to not only how the reactions are going to progress, but also predicting what products it's going to make. So that's the key. The reason why an alkane will undergo a free radical substitution and not a nucleophilic substitution comes down to the fact that it's not really that polar. So you should be familiar with this concept now, but alkanes have carbon-carbon and carbon-hydrogen bonds, which are relatively unpolar. Haloalkanes, however, will have a carbon-halogen bond. The halogen is quite electronegative. This will create an unequal distribution of electrons, thus giving the halogen a slightly negative charge and the carbon a slightly positive charge. The nucleophile, which is, as you can recall from the last slide, a negatively charged group that willingly donates an electron pair to form a bond, will attack, if you like, this carbon here that has a slightly positive charge, because nucleophiles are negatively charged and they like positively charged things. Now, carbon can only form 4 bonds. It's already got, I'll redraw this here. So if I have carbon and chloride and pretend it's bonded to 3 hydrogens here. If the nucleophile comes and attacks this slightly positively charged carbon, it's now got 5 bonds, which is kind of unstable, and we know carbon can't form 5 bonds as it's got 4 valence shells electrons. Essentially what will happen is this halogen, it will sever this bond, and this halogen will leave as a leaving group, and that is kind of the difference in the mechanism between a free radical and a nucleophilic substitution. Don't really worry too much about that yet. We'll show that a bit diagrammatically in the next couple of slides, but from this slide, I just want the takeaway to be that alkanes will undergo a free radical substitution and a haloalkane will undergo a nucleophilic substitution. To jog your memory, I've just taken the slide from the reactions of alkanes, alkenes and alkynes video, and this is a classic example of an alkane undergoing a free radical substitution. So you may recall, with UV light, we would split this bond up and create 2 chlorine free radicals. And this is how we draw the chlorine free radicals. Essentially what happens is, chlorine attacks one of these hydrogens, takes its place, this hydrogen leaves as a leaving group, and then bonds with the other chlorine free radical to give you hydrogen chloride and your chloroalkane here. Now hopefully you've had a brief refresher on free radical substitution reactions. Now we'll be going over the crux in understanding what haloalkene and haloalkene reactivity lies, and that is nucleophilic substitution reactions. So like I said, the haloalkane has the halogen group, and thus, due to the electronegativity of this halogen group, there is an unequal distribution of electrons, so the electrons like to hang around this halogen, giving this halogen a slightly negative charge and this carbon here a slightly positive charge. Due to this reactivity, it is prone to nucleophilic attack. Nucleophiles, if you recall, are slightly negatively charged or negatively charged molecules that are willingly able to donate an electron pair to a slightly positively charged area. In this case, the carbon here. So the nucleophile is willingly going to attack this carbon here. If we refer back to the previous slide, this alkane is relatively nonpolar. If we were to introduce a nucleophile, so this is our nucleophile here, there is no place this nucleophile could readily attack, no carbon this nucleophile could readily attack. Because all of them, none of them are slightly positively charged, they're all relatively nonpolar. So thus, if we want a substitution reaction to occur in alkanes, we need free radicals. Now we'll come back here. So basically, the nucleophile will attack this haloalkane from behind and form an intermediate bond. And that's what I'll show here. I'll just draw a squiggly line to show that intermediate bond. Now, the carbon's in a strange position because the nucleophile has readily donated 2 electrons or electron pair, and now it's got 5 bonds. And carbon has 4 outer shell electrons, it can't form 5 bonds. So what will happen is, it'll kick off this chlorine as a leaving group. And so you get Cl-, and the nucleophile will take the place of the original halogen. And that is where the crux of haloalkane substitution reactions lie. If you compare and contrast this with the reaction of the alkane, where you have the free radical, sure, one of the free radicals takes the place of the hydrogen. However, this hydrogen then forms a bond or a bond with the other free radical, and then you have hydrogen chloride. However, with the substitution reaction involving a nucleophilic substitution, this isn't entirely the case. The nucleophile straight away just takes up or takes the place of the halogen, and there is no hydrogen that bonds with the halogen. So the halogen is left by itself. It's a Cl-, which is a bit different to what happens in a free radical substitution reaction. So over the next couple of slides, I'm going to be showing you the different type of reactions that haloalkanes can undergo. So there are 2 types. They can either undergo a substitution reaction or an elimination reaction. This substitution reaction is always going to be of the nucleophilic type. Primary haloalkanes can undergo, or will most likely undergo, these nucleophilic substitution reactions. Secondary haloalkanes will undergo both the substitution reaction of the nucleophilic type and the elimination reaction I talked about, and tertiary haloalkanes will only undergo the elimination reaction and will not undergo substitution reactions of the nucleophilic type. So the first reaction we have is a reaction with sodium hydroxide. Primary and secondary haloalkanes will react with sodium hydroxide in an aqueous solution to give the corresponding primary or secondary alcohol. Now I've got a general formula for the reaction below, but we'll go over it more diagrammatically below. So with sodium hydroxide, you have sodium. It splits up like this in an aqueous solution. Now, you might recognize this in the original nucleophile, electrophile, and free radical slide. So OH is the nucleophile in this reaction. So, like I said, primary and secondary haloalkanes will undergo nucleophilic substitution. If we introduce sodium hydroxide, the hydroxide being the nucleophile, it'll undergo that nucleophilic substitution. So that's what I've got here. So the hydroxide part of the sodium is going to attack this carbon due to the electronegativities, form an intermediate bond, which I'll show a bit more nicely here. And then the chlorine is going to leave as a leaving group. And that is what you have here. So the hydroxide kind of takes the place of the chlorine, and the chlorine jets off. And you have all this sodium left off from the sodium hydroxide, and that the sodium chloride will form the irregular table salt, which is dissolved in the aqueous solution. So main takeaway, primary and secondary haloalkanes, when reacted in an aqueous solution of sodium hydroxide, the hydroxide will act as your nucleophile, attack the primary or secondary haloalkane, and give you a corresponding alcohol. And the chlorine, I should add, is your leaving group. Cl- is your leaving group. That's the byproduct. Another substitution reaction that primary and secondary haloalkanes can undergo is one of that with ammonia. And that'll give you a primary and secondary amine. So recall that amines have the functional group NH2. Ammonia, you may recall, I've drawn the structure of ammonia in the top right hand corner here, is NH3. You may recall ammonia from our discussion on acids and bases, with ammonia being a weak base. However, it is also a nucleophile. Although it's not negatively charged, it does have these outer shell electrons that are readily available to donate to a slightly positive or electron deficient area, such as the carbon in a haloalkane. This reaction, or a substitution reaction between a primary and secondary haloalkane and ammonia, will give you a primary and secondary amine, and the byproduct will be a halogen and halide. Now this is because ammonia is NH3. Two of those hydrogens, if you like, are used to make the amine functional group, so NH2. Now we have another hydrogen that's left over. This hydrogen is going to kind of bond with the leaving group, which is the halogen in the original haloalkane, to give you your halogen halide. And I'll show that a bit more diagrammatically in a stepwise reaction in the next slide. However, this is a general rule between a reaction between a secondary haloalkane, so notice how it has two alcohol groups, and ammonia to give you hydrogen bromide and this secondary amine here. So this is the same reaction shown a bit more diagrammatically. So we have ammonia here with its two lone pair electrons. Due to the difference in electron density, the carbon will take on a slightly positive charge and the bromine a slightly negative charge. Thus, this ammonia will attack this carbon and will readily form an intermediate bond with it. So you have ammonia, or the nitrogen here. You have hydrogen, hydrogen, and hydrogen. Now, both the carbon and the nitrogen are in a bit of a pickle. So the nitrogen would prefer to make about 3 bonds. So currently it's got 3 with the hydrogen. However, if it forms a bond with the carbon, it's now got 4 bonds. If you look at the carbon, it's now got 5 bonds when it originally had 4, so it's also unstable. So what they do is kind of shake hands and meet in the middle. So like with all nucleophilic substitution reactions, the nucleophile takes the place of the halogen, so the bromine boots out. So this is the intermediate that you have, so carbon. And the bromine's being booted out. However, this hydrogen also tags on with this bromine because nitrogen has 4 bonds when it would actually prefer to have 3. So you get the amine and you get the hydrogen halide as the byproduct. So that's the key takeaway. The main takeaway is that again, like with all nucleophilic substitution reactions between a haloalkane, yes, the nucleophile will take the place of the bromine. However, the reaction with ammonia is a bit unique in that the bromine leaving group also steals a hydrogen off the ammonia to give you the hydrogen halide. That's the main takeaway. So the very last reaction that a primary and secondary haloalkane can undergo is a reaction with cyanide or the cyanoion once it's dissolved in water to form a nitrile. And recall that a nitrile is this functional group here. Forgot the triple bond, that functional group there. So looking at the cyanoion, you should be immediately thinking nucleophile. That's a nucleophile. The second dot point we'll be covering in a bit more detail on another video. But however, nitriles, once you form the nitrile by reacting the primary and secondary haloalkane in the cyanide, that nitrile you can hydrogenate using hydrogen gas and a platinum catalyst to make amine. So this is just another way you can make an amine. Refer back to the previous slide, that's another way where the haloalkane reacts with ammonia to give you an amine. This is just a different way. So in chemistry, you should not just be memorizing these reactions straight off the bat, but having an appreciation of the understanding and how in real practice we can make these compounds. So here we have the reaction with cyanide. I've got a primary haloalkane here, but if you revert back to the slides on the types of reactions, these substitution reactions you should remember can occur between primary and secondary haloalkanes and the relative reactants. So that's the main takeaway. Although I've got a primary haloalkane here, it could very well react with a secondary haloalkane as well. However, for simplicity's sake, we have the primary haloalkane because the presence of another alkyl group wouldn't really affect the final product except the presence of another alkyl group. Like always, with all these substitution reactions, it comes down to the electronegativity of the halogen. So due to the intense electronegativity of the halogen, it will take on a slightly negative charge and the carbon a slightly positive charge. So thus, it's prone to nucleophilic attack. The cyanoion forms an intermediate bond. The bromine leaves as a leaving group to give you Br- in an aqueous solution. And thus you have this stable the stable compound here, which is your nitrile. And you have Br- as the leaving group. So at the very start, I said that haloalkanes undergo 2 types of reactions. The first one is a substitution reaction of the nucleophilic type, and the second reaction is an elimination reaction. Now we'll be going over the elimination reaction. These usually only occur between tertiary haloalkanes or secondary haloalkanes to a lesser extent, but it will usually be a tertiary haloalkane. Now, there's a key distinguisher present in this slide. So a tertiary haloalkane will react with sodium hydroxide to give an elimination reaction to form an alkene. The sodium hydroxide in this case needs to be dissolved in alcohol. Primary and secondary haloalkanes will react with sodium hydroxide to give you a nucleophilic substitution reaction to give a primary and secondary alcohol. However, the sodium hydroxide needs to be in an aqueous solution, and we have covered this reaction a couple of slides ago. The main takeaway I want you to understand is, if you see in an exam setting a tertiary haloalkane and the sodium hydroxide is dissolved in alcohol, it'll undergo an elimination reaction to form an alkene. If you see a primary or secondary haloalkane reacting with sodium hydroxide in an aqueous solution, it'll undergo nucleophilic substitution to give you a alcohol, a primary or secondary alcohol. That's the main takeaway. So I've got two images here. In both cases, we have a tertiary haloalkane reacting with sodium hydroxide dissolved in alcohol. So as you know, that'll create an elimination reaction to give you an alkene. So that's your main takeaway. However, the first image kind of goes over the reaction mechanism, which we'll explore in a very brief detail because it's outside the scope of your syllabus to understand it in great detail. And the second goes over a little more of an interesting or abstract point that we'll go over in a later slide. So basically what happens is, in very, very brief terms, if the hydroxide group of the sodium hydroxide will come, and instead of attacking the carbon, which happened in the nucleophilic substitution reactions, will attack the hydrogen in this case and kind of steal it off. So the OH and H will leave off as water. So that's the main takeaway. Now there's 2 electrons here that were being used up to form that carbon-hydrogen bond. They're no longer being used, so they kind of form a double bond here between these 2 carbons here. Now, this carbon here is in a sticky situation. It's got a double bond here, it's got a single bond here, and it's got a single bond here and a single bond here. So in total, it has 5 bonds. So what it'll do is, as it always does, boot off the halogen as a leaving group. So the final product is, I'll just rub that out again. So the hydrogen's left with the OH to give you water. The bromine's left to give you Br- in an aqueous solution, and thus the only thing you have is this alkene here. Now, I'd like to propose to you a question. This is a relatively simple example in which the double bond could only take one place. So realistically, it could only take one place here. However, if we look at the example below, there are 2 possible places a double bond could form. Why specifically does it form in this position as opposed to this position preferentially? I'll give you a moment to think about that. So before we continue with the next slide, it's really important you understand the products of the reaction as well. So although you get the alkene from the original haloalkane, you also get water and Br- or the negative ion of the halogen leaving group as the product. So that's the key thing. You get the alkene, water, and Br-. And hopefully with the reaction mechanism, you've understood why we get those 3 things. Now, to predict where the double bond's going to form, we need to apply something called Zaitsev's rule. Now, if you're after just the high yield content, this is outside the scope of the syllabus, and there is no practical reason as to why you would get examined on this or need to know this. However, if you're generally curious or like chemistry, I recommend you stick around and follow along with this explanation. Now, once this Russian chemist called Zaitsev, he reacted this molecule here in sodium hydroxide in an alcoholic solution. Now, if we look at this carbon here, this is an example of a secondary haloalkane. If we have sodium hydroxide in an alcoholic solution with a secondary haloalkane, it'll give us an elimination reaction. And that's kind of what he found. However, he found that there was 2 products. There was a major product. So this product was actually formed 9 times more than this product up here. And the only reason why they differed is there was a difference in where the double bond was. In one, it was just on the right-hand side of the carbon, on the other, that was on the left-hand side. However, this one formed, the one that was on the left-hand side, formed vastly more than the one that was on the right-hand side. Now, why is that? What sides have proposed, well, the easiest way to remember it, I find, is that the poor get poorer and the rich stay richer. If you recall from the reaction mechanism, the OH comes and kind of attacks one of these hydrogens. However, it can come and attack a hydrogen on either side of the halogen, right? So it can attack this hydrogen here or this hydrogen here to leave and form water. So that's the first step in the reaction. Now, which one is it going to be more likely to attack? The answer is the carbon with the lowest amount of hydrogens. So this is your central carbon with the halogen. This carbon here has 2 hydrogens. This carbon here has 3 hydrogens. So it's going to attack this hydrogens preferentially more. I'll draw that a bit nicer. So it's going to attack this hydrogen preferentially more because that carbon is only bonded to 2 hydrogens. So thus, it'll take this hydrogen away. That'll form your leaving water. This bond will form a double bond here. So you get a double bond here. And then this carbon is in a sticky situation because it's now got 5 bonds, and that fluorine, as you may recall from the previous slide, will leave off as Fe-. So thus, that'll give you the major product. And you also have H2O and F- in an aqueous solution as the byproducts to that reaction. That's kind of the main takeaway. All you need to understand from Sidestep's rule is, if you do choose to remember it at all, is that the poor get poorer. So the carbon with the lowest amount of hydrogens is the one that's going to be attacked. So in this case, it's that one. And then that is the side where the double bond will form.